Christian Garay from the University from Paris 6. And he will be speaking about the fundamental theorem of tropical differential algebraic geometry. Christian?
First of all, thank you to the organizers for inviting me to give this talk. This talk will be about a humble result that we got like 3 months ago, and I want to talk about it here. So the plan of the talk is mainly distributed among 3 parts. The first part is the introduction. I will talk about what is known by some people as the fundamental theorem of tropical algebraic geometry. Then I will introduce the differential part or differential aspect of this statement. Right after that, I will talk about some preliminaries about differential polynomials and their set of solutions. Then tropical differential polynomials and also their sets of solutions. And then I will discuss 2 tropicalization morphisms. And to finish, the third section will be, I will talk about the proof of this result. I will clearly state the problem. Then I will discuss some ideas about jet spaces for differential ideals. And finally, a sketch of the proof. First of all, I have to mention that this is joint work with Santa Rota and Seinat Togani from Cuernavaca in UNAM. Sorry. So in the introduction, I will give a quick review of the fundamental theorem of tropical algebraic geometry, and I will talk about its differential version. Let me start by introducing the tropical semifield. If some of you don't know it, it's just air R with infinity and 2 operations. This operation, a plus inside the circle, will be the minimum, and the dot inside the circle will be the sum. And I will consider a tropical Laurent polynomial there. So the tropical hypersurface, or sometimes called bed locus of tropical polynomial like here, consists of the set of points where the value of this function, as a function from Rn to R, is reached at least 2 distinct monomials. This is the bed locus of the polynomial, is the set of points such that this value is reached at 2 different monomials, for some j different from k. Each bed locus of a tropical polynomial is the support of an rational polynomial complex of pure dimension n-1 in Rn. For example, let's consider this tropical polynomial in 3 variables. And if we compute the bed locus of this tropical polynomial, this is the picture that we are going to get. Let us consider a real valued field, here k, together with a real valuation. And I will consider an ideal of the ring of Laurent polynomials over k. And I will construct what this morphic tropicalization is classic. We take a polynomial here, and the only thing we do is we send these coefficients from k to r using the valuation, and we change plus with mean, and we change products with the tropical multiplication. So the tropical variety induced by the tropicalization of an ideal is the intersection of the bed locuses, loci, of all the tropicalizations of the polynomials in the ideal. So this is this may be an infinite intersection. On the other hand, the tropicalization of the non-Archimedean amoeba of this closed-loop scheme inside the torus can be defined as the image of the points, of the L points of this closed-loop scheme, where this field together with this valuation is a valued extension of the base field with two conditions. The first condition is that L has to be algebraically closed and W has to be a non-trivial valuation. So this setting is really general, because here we are just demanding that this field to be real value. It can have any characteristic and the valuation can be trivial. So what is known by some people as the fundamental theorem of tropical algebraic geometry is that the tropicalization, the tropical variety induced by the ideal, which is this intersection, coincides with the non-Archimedean amoeba of the closed subscheme.
Okay.
So I will now switch to the differential part. So remember, this is the theorem. You take your valued field, real valued field, and you take an ideal inside the ring of Laurent polynomials. Then the tropicalization of the variety consists the non-Archimedean amoeba of the closed subscheme. What we did is to prove an analogous statement for the differential algebraic setting. This is, we need to consider these ingredients. We have to define the set of tropical differential polynomials. I will do it in a minute. I will consider the ring of formal power series with in one variable together with the order valuation and with the usual differential structure here, the usual differential. This is a differential real valued ring of formal power series over an algebraically closed field of characteristics 0k. This is going to be fixed for all the talk. I will consider a differential ideal, which is just an unusual ideal, which is closed under the differential operation. And I will construct a tropicalization morphism that will send a differential polynomial here to a tropical differential polynomial. I will introduce that later. I'm just giving the ingredients. I will define the tropicalization, the set of solutions of the tropicalization of a differential ideal as this. This is a copy from the definition of the tropicalization of a variety induced by an ideal. I will define this set, sol phi, which will be the set of solutions of a tropical differential polynomial. This will be an analog of the tropical hypersurface of a tropical polynomial. I will define also the set of solutions of I, which is a differential ideal in a ring of differential polynomial, as the points in the ring, the n-tuples in the ring, such that this point annihilates every polynomial in the ideal. And I will define its tropicalization of this set as the support of all these series. This will be a differential analog of the non-Archimedean amoeba of a Laurent ideal.
What is Laurent ideal?
An ideal in the Laurent ring, the ring of Laurent polynomials. And the theorem that I want to show, or I want to discuss about, is that the solutions of the tropicalization of a differential ideal will be the tropicalization of the solutions of the ideal. So this is a copy of the previous statement. If I can just go back quickly now. Yeah, it's not working anymore.
No, es que debí decirte cómo usar el láser porque se acabó la batería con el láser.
I'm sorry.
No.
So this is the project of the talk. This is just an introduction. I will formally now introduce the objects. So we pass to the second part of the talk, preliminaries. I will introduce the differential ring of differential polynomials over this ring. and the set of solutions of a differential polynomial. Then I will talk about the set of tropical differential polynomials and the set of solutions of a tropical differential polynomial. And I will introduce two tropicalization morphisms to link these two ideas. So let's talk about differential polynomials and their set of solutions. I will consider always as R the ring of formal power series in one variable over an algebraically closed field of characteristics 0k, together with the order valuation and the classic differential. The ring of differential polynomials is denoted like this. It's a differential extension of this ring, constructed using this ring in infinitely many variables, and extending the differential by this rule. I will introduce.
What is the example we should think of? What is the main? What is the classical example that satisfies this? Can you give me an example of a ring with differential?
It's just.
What are you trying to model?
To just take as a ring you take this.
Yes, but the differential is equally maps one to the next. What is that you're trying to model?
This is intended to be the G differential of the xi variable. And when you make this switch, this translation, you are saying that the differential, the J differential becomes the J plus 1 differential.
The J partial differential.
Yes, in the xi variable.
Equation. What needs to be
Yes. These are intended to be symbols which model polynomial differential equations. So I will introduce what is a differential monomial in order to simplify the discussion. A differential monomial is a formal expression which is built using a matrix with entries in C in the non-negative integers and of dimension n times n plus 1. Right? It's just a product of variables, and dj keeps track of the order of the derivative, and this is the power of that order of the derivative. So each differential monomial induces a map from the ring, from the n-fold product of the ring to the ring, just by putting in this xij variable, we put the j differential of the phi of the nth element here. So this gives us a map from here to here.
But this action of the differential is localized. How is it what's the action on here? There is the classical one. What is the action on here? So see that
R is this ring.
It's already differential.
It's already differential. In order for this to have sense, you have to work in a differential ring.
But you have some kind of product of differential polynomial, the usual one.
Yes.
Bicycle. So you want to be differential with some optimization or just
No, the differential is the classic differential in this ring.
bicycle. So differential, for example, is n times s. So
Yes. So we have this mapping and the set of solutions of a differential polynomial. I can write a differential polynomial as a finite formal sum of differential monomials like that. And the set of solutions are just n tuples in Rn such that the polynomial has phi as root.
the solution of the differential equation?
A solution of the differential equation is set in power series.
but he's no is another R is bigger number, so R
No, R
No,
is
it's
my
KT.
ring.
The formal series of T.
So it just means a
I should mention that for me R is always going to mean that ring with that order and with that differential. But in fact, this is a short version of what is a algebraic differential manifold, because using a differential polynomial, we can define a differential algebraic hypersurface as the set of zeros, right, of this polynomial, but looking at points which are in a differential extension of the field of fractions of R with the traditional differential. So this set that we are defining here is just the R points of this hypersurface. L is a differential extension of the field of fractions of R. So this is a general concept. In fact, if you have a differential ideal, you can construct an algebraic differential manifold by looking at all the solutions in all possible differential extensions. And I'm just looking at the R points. That's what I'm calling the set of solutions of a differential polynomial. So I will talk now about tropical differential polynomials and their sets of solutions. Remember that T is the semi-field of tropical numbers, tropical semi-field with these operations. So a natural way to define tropical differential polynomials is just to change the operations from classic to tropical. So this is what I'm doing here. I'm introducing tropical differential monomial as a formal expression like that, where this dot means sum, this dot means sum also, right? So it's just copying the concept that we had previously from classic city. So a tropical differential polynomial is a finite sum of these guys, right? And I want to associate to any tropical differential polynomial here a solution set, which is going to be a subset of the power set of the non-negative integers to the n. So let's see this definition given by Tim and Grigoriev this year. I take a subset of non-negative integers, and I can define this mapping that may seem kind of difficult. For example, if I consider the subset, defining subset 1, 2, 1, 3, 4, I can define val S of 2 as the minimum in the subset, which is bigger than 2 or equal than 2 minus 2. So here, this number is 3 minus 2 is 1. And if there is no such value, I define the value of the function as infinity. No, this comes from the classical setting. If we take a power series, and if we take S as the support of the power series, then this is just the order of the J differential of the power series. No, just take a series, take the derivative J times, and then take the order of the result, and that's just an abstraction of this operation. So I will take an n-tuple of subsets of the non-negative integers to the n, and I will take a tropical differential monomial, and I can define this number, right, using the previous definition. And using this definition, I will say that this n-tuple is a solution of this tropical differential polynomial if either there exist two monomials such that this minimum is achieved at these two monomials, different monomials, or if the value of the substitution is equal to infinity. I will now introduce tropicalization morphisms. Once again, let R be that ring. I will now define two morphisms of tropicalizations. The first one is going to take a classical differential polynomial and it's going to transform it into a tropical differential polynomial. And the second is going to take an n-tuple of series and it's going to transform into an n-tuple of subsets of non-negative integers. So the tropicalization of a polynomial, we take this tropical differential polynomial and we just take the order of the coefficients and we change the differential monomial into the corresponding tropical differential monomial. And tropicalization of an n-tuple here is just the support of each element. We have to notice that this second tropicalization is very different from the usual one, because the usual tropicalization is just a first order approximation, and here we are taking the whole support of the series. With these definitions that I have just given, we have that if I take a solution of a differential polynomial, then its tropicalization is going to be a solution of the tropicalization of the polynomial. And this implies that for any differential ideal in the differential ring of differential polynomials, I have a morphism that transforms each solution here into a solution of the tropicalization of the ideal. So the question that was raised by Grigoriev earlier this year was, if I have a differential ideal and I have an n-tuple of subsets of non-negative integers, which is a solution to every tropicalization of differential polynomial here, does there exist a solution to the whole ideal such that the support of this solution is exactly this tropical solution? So it's kind of an inverse problem. And this is the problem that we solve. So to finish, I will give some words about the proof. In particular, we have to discuss jet spaces for differential ideas here. So what we have to show is that this subset is contained in this set is contained in this set, which is to say that this morphism is surjective. The proof is technical and it consists of two main steps. The first is to go from this differential, or this product of differential ideas to this infinite affine space, while preserving the differential structure from Rn. And second is to go from this space, infinite affine space, to a finite algebraic torus that depends on the particular S that we are going to take here or there. So the first step, how can we go from Rn to this infinite affine space while preserving the differential structure? This has to be with some extension of definitions and results from theory of arc spaces to differential ideals in this ring. And this is the key lemma. If we consider this bijection, just dividing, we will have to divide by j factorial here. Then, when we do this bijection and we evaluate in a differential polynomial, we obtain this expansion. Right? This is a differential polynomial, and these are the successive derivatives of the polynomial evaluated at t equals 0. An extension of a well-known fact that then we can always find a finite subset of this differential ideal such that the whole set of solutions of G is just the finite intersection of the set of solutions of this finite subset. And this is an easy application of a technical result known as Reed-Roden-Bush basis theorem. So I will now take a differential ideal and take these S elements in G such that the whole set of solutions is the intersection of these finite the sets of solutions of this finite set of elements. And I will define these polynomials as being the k derivative of the L polynomial evaluated at 0. And I will consider the set of solutions of all these polynomials in this infinite affine space. Then we have successfully transformed our problem from one problem over Rn to a problem in this affine infinite space, right? Because the image of this algebraic set under the bijection that I introduced before is just the set of solutions of the differential ideal. Then what we do is we define an inverse system, like in the traditional arc spaces or traditional ideals, such that this space is the inverse limit of these arc spaces for differential ideals. And here is an explicit description of each AM. So I put at AM the number of differentials that I'm taking, right? And I compute the set of solutions of this algebraic system in some finite affine space. Now I will take an integral of positive of subsets of non-negative integers, and the second step is to go from this infinite affine system, this infinite affine space, to a finite algebraic torus that depends on this subset. So we consider the torus supported on S. I am just keeping the coordinates that appear on S, and I am factoring by the coordinates that do not appear in S. And I intersect the previous set of solutions with this infinite torus. Then once again I have I can define an inverse system such that this set of solutions in the torus is going to be the inverse limit of these jet spaces. And we show finally that the whole system will be non-empty if and only if there exists an index such that this partial subsets is empty. So to finish the proof, we just take a subset which is not in the tropicalization of the solution of G. Then I know that there exists an index such that this space is empty. And we use Hilbert and Stellensatz to construct an explicit element such that this element is not in the solution of the tropicalization of G, showing that S is not a solution of the tropicalization of the whole ideal, and this finishes the proof. The next question is whether or not there is a tropical differential analog of a tropical basis. What is a tropical basis? Is if I give a differential ideal, can I find a finite subset of elements in G such that the whole solution system of this tropicalization is just the intersection of the solution sets of these polynomials? And finally, if such basis does exist, the next question will be to find bounds on it. So just a final word. We use the word tropicalization because we are in this differential setting. We are interested in knowing the supports of solutions of differential equations. contrary to the first order approximation that is used in classical tropicalization. Thank you.
Do you have any questions? And you do?
Can you give me some applications of your theorem or the motivations? You mentioned one motivation
Yes.
for this type of
The
research.
motivation from Grigoriev was to keep track or to know the supports of solutions of polynomial differential equations. So this theorem ensures you that if you find a solution, a support, a set of supports that is solution to all the tropicalizations of the differential ideal, then there exists a solution to the whole idea, whole differential idea, which has support this tropical solution. So we solve the inverse problem. When the tropical answer gives you a traditional answer, in this case, it gives you just the support. You have to look for the actual coefficients, but the support is already something.
Thanks. Any other questions?
I have some point, but what was the jets that you were talking about? Because you took in the beginning,
Yes.
I failed to see where they appear.
Más para acá. No, más para adelante. Más. Yeah. So the jets that we define are just the solutions of this system of equations in some affine space. The problem with the differential setting is that your affine space may be larger than Kn. In the traditional setting, the jet space, the zeroth jet space lives in Kn for an n-dimensional variety. And the second lives in K2n, and the third in K3n. But here, the zeroth jet space may live in K5n, and the second in K16n, for example. So it's just, you just have to add more variables, because you will have here differential. You will have here several other variables which are meant to be differential. But you can treat them as algebraic variables.
Any other questions?
I have one. Like, in your proof, it seemed essential to have the characteristic zero.
Yes.
But do you?
Yes, because several theorems that we used for the development of the differential part depend strongly on characteristic zero.
So
For
there is no proper characteristic Z for this.
I don't know, because for example, this theorem is made for characteristic zero. Otherwise, I don't know if you can, if given a differential ideal like this, I don't know if the characteristic is positive. I don't know if you can find, you will be able to find a finite set of generators. But in characteristic zero, this theorem tells you that you can do it, and then you can proceed to prove this result.
Any other questions? Thank you very much. And we continue in 15 minutes.